to the explainer. Have you ever looked at a complex math problem and just felt like it was a completely random jumble of digits? Honestly, I think we've all been there at some point. Well, today, we're going to change that entirely. We're decoding the hidden rules of real numbers, specifically diving into the core concepts from exercise 1.1. By the end of this explainer, you're not going to see numbers as just random symbols anymore. You'll see them as structured, predictable, and honestly kind of beautiful building blocks. Let's get right into it. Okay, so here's our agenda. This is our exact roadmap for mastering this mathematical toolkit. We'll hit prime factorization basics, then finding HCF and LCM, move on to the golden math formula, explore some properties of numbers, and finally, wrap up with real-world applications. All right, section 1, prime factorization basics, the mathematical building blocks. Now, the absolutely crucial point here is this definition, prime factorization. Think of prime factors as literally the DNA of any number. Just like a really complex molecule is built out of basic atoms, any composite number is just a combination of prime numbers. Those special numbers that can only be divided by 1 and themselves. Let's look at question 1, part 3 to see this in action. We're going to systematically divide the number 3,825 to reveal its prime sequence. So we always start by checking the smallest primes. It's an odd number, right? So 2 won't work. We try 3 and boom, we get 1,275. Let's divide by 3 again, and that hits 425. Now 3 doesn't work anymore, so we move up the ladder to 5, which gives us 85. Divide by 5 one more time, and we land right on 17. And hey, 17 is a prime number itself, so we're done. And this right here brilliantly illustrates the final, elegant form of those building blocks. Instead of writing out this super long, clunky multiplication string, we just group them together using exponents. So the 2 3s become 3 squared. The 2 5s become 5 squared. And the 17? Well, it just stands alone. We have successfully extracted the DNA of 3,825. Moving right along to section 2, finding HCF and LCM, extracting relationships. Now, what's really fascinating here is how clearly the strict, common-only rule of the highest common factor, the HCF, contrasts with the all-inclusive rule of the lowest common multiple, the LCM. Let's look at the numbers 12, 15, and 21. Think of the HCF as the picky one. It only wants a prime factor if it exists in all 3 numbers. In this case, that's literally just the number 3. The LCM, on the other hand, is a total collector. It grabs the highest power of every single prime factor that appears anywhere on the board, the 2 squared, the 3, the 5, and the 7, and multiplies them all together to get a massive 420. Okay, section 3, the golden math formula. This is the ultimate check. What you're looking at right here is the golden formula. It's a foundational concept from question 2, and honestly, it's the ultimate verification tool. It tells us that if you take the LCM of 2 numbers and multiply it by their HCF, the result will always, and I mean absolutely always, be exactly the same as multiplying the original 2 numbers together. It feels a bit like magic, but I promise you it's pure mathematical logic. Let's actually test this out, right? We'll apply this formula to the numbers 5, 10, and 92 just to see the magic happen on both sides of the equation. So we found their LCM to be 23,460, and their tiny little HCF is just 2. On the other side of our equation, we simply take our original integers, 5, 10, and multiply it by 92, multiply them both out, and yep, we get exactly 46,920 on both sides. This proves beyond a shadow of a doubt that our golden formula holds true. Seriously, this is the ultimate built-in answer checker for your math problems. If both sides don't perfectly match, you instantly know you've made a calculation error somewhere in your prime factorization. And as shown in question 4, we can actually get creative and use this formula in reverse to find a missing LCM without having to do any long, tedious factorizations. Say we know our 2 numbers are 306 and 657, and we're told their HCF is 9. We literally just plug those into our golden formula, do a quick division, and instantly reveal the LCM as 22,338. It just saves so much time. All right, section 4, properties of numbers, theoretical proofs. Now, this is a super intriguing question from the source material. It asks us to predict the behavior of a number raised to any power, which kind of seems impossible until you know the hidden rule. If you take the number 6 and raise it to the power of any natural number n, 6 squared, 6 cubed, 6 to the power of 1,000,000, will that final calculated number ever end with a 0 in the ones place? Well, the big aha moment lies right in the prime factors themselves. Think about it. To end in a 0, a number's prime DNA has to contain at least 1 2 and at least 1 5, because 2 times 5 equals 10, right? But look closely at the number 6. Its prime factors are only 2 and 3. Because the number 6 completely lacks the prime factor 5, it is mathematically impossible for 6 to the power of n to ever end in a 0, mystery solved purely by looking at its prime factors. Similarly, in question 6, we're asked to prove why a massive, messy mathematical expression is a composite number rather than a prime number. Well, by simply factoring out a common 13 from that huge string of numbers, we show that the entire expression can be rewritten as 13 multiplied by 78. Because it has factors other than just 1 in itself, we instantly prove that the result is absolutely a composite number. Boom, done. Finally, Section 5, Real-World Applications. This is math in motion. Okay, I want you to imagine a sports track where two runners, Sonia and Ravi, are moving at different speeds. They both start at the exact same point, at the exact same time, going in the same direction. The big question is, how can we predict exactly when their paths will cross again right at that starting line? Well, by breaking down their lap times into our trusty prime factors, the seemingly random nature of their running speeds actually becomes highly predictable. Sonia takes 18 minutes to complete a lap. Ravi is a bit faster, he takes 12 minutes. So we just find the prime factors for both 18 and 12. And here's the crucial point. This physical, real-world word problem, it's literally just an LCM extraction puzzle wearing a disguise. We just need to find the lowest common multiple of their lap times to pinpoint that shared moment in the future. We pull the highest powers from our prime factors, 2 squared and 3 squared. And there we have it. Multiply 2 squared, which is 4, by 3 squared, which is 9. Calculating the LCM of their times tells us that after exactly 36 minutes, Sonia and Ravi will perfectly align right back at the starting line. Sonia will have finished 2 laps, and Ravi will have finished 3. But right at minute 36, they cross the start together. So, once you learn to see the world through this lens of prime factors and LCMs, you quickly realize that math isn't just something you do for homework. It's actually the secret code to how everything around us connects. From runners on a track to predicting planetary alignments in space, these foundational rules are literally everywhere. So, what other hidden everyday patterns will you decode next? Keep asking questions, keep looking for the structure beneath the surface, and thank you so much for joining me for this explainer.